Hello everybody and welcome back. We're going to continue our look at the 2011 Friar Contest. So we're on to question number 3. Begin with any two-digit positive integer and multiply these two digits together. If the resulting product is a two-digit number, then repeat the process. When this process is repeated, all two-digit numbers will eventually become a single-digit number. Okay, so they're telling us that there are no cycles. Once a product results in a single digit, the process stops. For example, if we start with 97, we take the 9 and the 7, we multiply them together, we get 63. Then that's a two-digit number, so we take the 6 and the 3, multiply them together, we get 18. 1 times 8 is 8, so the process stops at 8 after 3 steps. So each transition period is a step. Okay, 48 gets us 32, then 6, and 50 goes 5 times 0 is 0. Okay, process stops after 1 step. Alright, so we have 4 parts to this question. A, beginning with the number 68, determine the number of steps required for the process to stop. Okay. So 68 goes to 6 times 8, which is 48. 48 goes to 4 times 8, because it's still a two-digit number, so we continue on with the process. We get 32. 4 times 8 is 32. So that's step 1. Step 2. 32 goes to 3 times 2, which is 6. So the process stops at 6. So we know we're going to end at 6, and more importantly, we know that it took 3 steps, and we were asked to determine the number of steps required for the process to stop. So 3 steps. They're introducing us to the idea of counting how many steps things take. Alright, B. Determine all two-digit numbers for which the process stops at 8 after 2 steps. So now that we have the notion of steps under our belt, we're going to figure out how to exactly stop at 8 after only 2 steps. Well, if I achieve 8 from a two-digit number, I'm going to have the digits of that two-digit number be factors of 8. So 1 times 8, for example. So we need single-digit factors of 8. This is important because if we were to do like, 22 or something, we couldn't have 2 times 11. Because otherwise, what's our two-digit number that gave us the 2 and the 11? Makes no sense. So we need single digits. So 8 can be either 1 times 8, 2 times 4, 4 times 2, or 8 times 1. So before 8, we can have 18, 24, 42, or 81. So each of these stops after 1 step at 8. Now we want the number of digits that stops at 8 after 2 steps. So 18, 1 times 18, that's not going to do it. 2 times 9, 3 times 6, 6 times 3, and 9 times 2. 24. What single digit product gives us 24? 1 times 24? No. 2 times 12? No. How about 3 times 8? Absolutely. 4 times 6? You bet. 6 times 4? And 8 times 3. How about 42? Well, there's only one single digit way to get that. That's 6 times 7. And 7 times 6, 81. Only one thing we can add here, and that's 9 times 9. So that tells us that 29, 36, 63, 92, 38, 46, 64. One thing we can notice is that order of the digits doesn't really matter. 83, 67, 76, and 99. Stop at 8 after 2 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright, so 11 numbers. We were asked to determine all 2-digit numbers which stop at the process, so we have 11 of them, and we've listed them out. Alright. C part. Determine all 2-digit numbers for which the process stops at 4. Okay, so we're going to have to do more backtracking, but this time we're not stopping after 2 steps. So, for example, 36. We got 36. Actually, we got 63 last time. 63, we could have gone back a step further, but then we would have been ending at 8 after 3 steps. So we're going to keep going and going for 4. Okay. So 4 is either 1 times 4, 2 times 2, or 4 times 1. Okay? So each of these guys stops at 4 after 1 step. Now 14, that can be 1 times 14, that's no good. 2 times 7, 7 times 2. So nothing works for 22. Nothing at all. Same with 41. There's no way to get 41 as a product of 2 single digits. It's a prime. So now we know who stops at 4 after 2 steps, 27 and 72. They both go to 14, which then goes to 4. Alright, but we're asked all the numbers that stop at 4, so we can't just stop at 2 steps. We're going to have to keep going. 27, we can write that as 3 times 9, and 9 times 3, and those are the only ones. 72, that's going to be 8 times 9, or 9 times 8. So after 3 steps, each of these 4 numbers will stop at 4. Okay. So 39, that's not going to work. 93, it's got a factor of 3 in there, but then it's 31, that's a prime, that's not going to work. 89 is itself a prime, that's not going to work. 98, it's got a factor of 7 in there, but it's 7 times 14. That's a no. So there's nothing further to move back. Nothing stops at 4 after 4 steps, and that means that nothing will stop after 5 steps, and so forth. So we were asked for all the numbers that stop at 4 eventually. So there, we have all the numbers that stop at 4. Okay, and none of them stop after 4 steps. It's 3 steps, 2 steps, or 1 step. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Okay. So that was C, determine all 2-digit numbers for which the process stops at 4. Now, D, determine a 2-digit number, okay, for which the process stops after 4 steps. So far we haven't really seen anything that stops at 4 steps. Granted, at 4 we could go back 3 steps, and 8 we can at least go back 3 steps for 8. We didn't really pursue it anymore. We just went back 2 steps and found all of those. But D, I determine a 2-digit number. Okay. So, this is a sort of question I'm not really a big fan of. There really isn't a good way to go about this. Or if there is, I have absolutely no idea how to do it. So if you got a better way, leave it in the comments. But this is a sort of, it just comes down to bookkeeping. There's no single digit we think this process might stop after 4 steps at. So we are going to have to take a look at all the single digits and work them all backwards and figure out if there's anything that stops at 4 digits. And it's going to just be a giant mess of just working things backwards, no rhyme or reason, no mathematical intuition, just factoring into single digits and working things out. So please, this is the way I'm going to do it. If you have a better way of doing it, please leave a detailed description in the comments, because I would love to know a better way to approach D part. But just determining a 2-digit number for which the process stops after 4 steps, I got nothing to go on. I mean, maybe we could just specifically try 8 because it's so robust, but there's no reason to try 8. We know it definitely won't work at 4. Okay? So we could ignore 4. That's the best we can really say. Okay, so we have to ask ourselves, what about the other single digits? We know it won't work with 4. How about 0? So 0, well, we can get 0 by doing 10, 20, 30, 40, 50, 60, 70, 80, and 90. Okay? Now these ones down here, they're not going to work. They're way too big. But this one, 40, can be 5 times 8 and 8 times 5. 30 can be 5 times 6, 6 times 5, and is that all it can be? Yeah, that's all it can be. You can't have a 4 or anything in there. We're going to have 4 times 5. So 45 could precede 20, or 54 could. Can't have a 3, can't have a 2. That would be 2 times 10. For 10, we could have 2 and 5, and 5 and 2. 25, that gives us 5 times 5, 52. That's a no-go. 45, well, that's 59, 95. So we get 1 step away. So we need to be 4 steps away from 0, if 0 is going to be our end digit. $54, that, I think that's 6 times 9. So we can have 69, or we can have 96. 56, that's 7, 8, 8 and 7. 65, that's 5 times 15, that's not going to work. 58, that's 2 times 29, that's not going to work. 85, that's 5 times 17, there's no way we can get that. So we get 2 steps. Okay, so 55, that's a no. 59, no. 95, that's way too big. That's 5 times 19. There's no way we can get 2 single digits that multiply to 95. In fact, anything over 81 won't work. So 69, that's 3 times 23. Nope. 96, that's automatically an X. I don't even need to worry about it because it's over 81. 78, that's 2 times 39, so that's 6 times 13. That's not going to work. And 87 is over 81, so it's an automatic X. So these guys all stop at 0 after 3 steps. Okay, that's fine. So 0 won't work. How about 1? Well, 1 is 1 times 1. And 11 is a big ol' X. So that's just 1 step. 2. Well, that's 1 times 2, or 2 times 1. So this is a little more promising. 12 is 2 times 6, 3 times 4, 4 times 3, and 6 times 2. 21 can be written as 3 times 7 or 7 times 3. All right. $26 is 2 times 13, so that's not going to work. 34, we had 43, we had 62, we had 37, and we had 73. Both of those are prime, so they're not going to work. 62, that's 2 times 31. That's not going to work. 43 is a prime, it's not going to work. 2 times 17, not going to work. So you can see what I mean. There's really no math involved here. There's no pattern recognition. We can add them in. The smartest thing we've said so far is that it can't be 4 from our previous work. And it definitely isn't going to be anything like... once we hit 81, we can't go any further back. That's the best we've been able to do. All right, 3. That's 1 times 3 or 3 times 1. both of those are prime, so they're not going to work. Four is done. How about 5? 1 times 5 and 5 times 1. Well, 15 can be 3 times 5, or 5 times 3. And 51 is, that's 3 times 17, so that's a no. So these guys here, 15 and 51, they stop after 1 step. 35, well, that's 5 times 7, or 7 times 5, so that looks promising. 53 is prime, so that's a no-go. So 57 will stop at 5 after 3 steps. And same with 75. And 75 is 5 times 15, or it's 3 times 25, and there's really no way to do that. 57 is 3 times 19. No way to do that as well. Alright, how about ending in 6? 6 is a more robust number. So we can have 16, we can have 23, we can have 32, and we can have 61. 61 automatically is not going to work, but 16, that's 2 times 8, 4 times 4, or 8 times 2. I have a good feeling about this one. 23, that's a no. 32, by the way, right, 61 is an X. 32, that could be 4 times 8 or 8 times 4. That's the only way to do that. These guys are 1 step away from 6. Let's do this on the next page. $28, $44, that's automatically an X. 82, that's over 81, that's automatically an X. What were the other ones we had? 48 and 84. Yeah, that's over 81, so that's an X. We don't need to think about that. That's 6 times 8, or 8 times 6. And 28, that's 4 times 7, or 7 times 4, and that's the only way to get that. And these are what, 2 steps away from 6? So we have 47, we have 74, we have 68 and 86. That one's an X. That's prime, so it's automatically an X. 74 is, 2 times 37, so that's not going to work. And 68, that's 2 times 34, so that's 4 times 17, so there's no way to get 2 single digits to multiply to that. Okay. So that was 6. We have digits 7, 8, and 9 to end up on left. I really hope it doesn't go all the way to 9, otherwise I'm going to be super, super angry. So we can have 17 or 71, both prime, so this isn't going to work. Alright, 8. Now 8, like 6 and 4, and this one might work a little better. We certainly have a lot of numbers we can try. 1 times 8, frankly I should just write 18. 18, we have 29, we have 36, we have 63, we have 92, and we have 81. Okay, so we've already seen bits of 8 already. I just want to go back and double check something. Okay. Why am I saying 2 times 8? Oh, 2 times... I was doing these ones down here. I was wondering why I was getting more numbers for 8 than I had previously. So I had to go back and check. So 8, of course, is not 2 times 9. I'm thinking 8 ahead to 18. 8 is 1 times 8. It is 2 times 4, 4 times 2, and 8 times 1. We already did part of 8, so this isn't a giant surprise. 2, 9, 3, 6, 6, 3, 9, 2. 24 was 3, 8, 4, 6, 6, 4, 8, 3. 42 was 6, 7, 7, 6. 81 was 9, 9. These are one step away. 29, that's prime, so that's not going to work. 36, 63, 92. 92 is over 81, so it's automatically out. Because there's no single digits that multiply to anything above 81. 38, 46, we'll do 64 over here. 83 is out. 67 is prime, so that's out. 76, 99 is automatically out. 76 is 4 times 19, so that one's out. 38 is 2 times 19, so that's out. 36, that's 2 times 18, so that's 4 times 9, 6 times 6, 9 times 4. 63 is 7 times 9, 9 times 7. 64, that's 8 times 8. And 46, that's 2 times 23, so that's out. Okay. Oh, I should have labeled those 2-step. So now we have 49, 66, 94, 79, 97, and 88. These are all 3 steps away from 8. 49, 66, 94, that's an X. We had, I know there was something else, and then there was 88. 79 and 97. That's out. That's prime. That's out. These two are both out because they're above 81. This is 6 times 11, so there's no way that's happening. And this is 7 times 7. And 77. That's 7 times 11. That's not going to work, but it is 4 steps. Nah, I'm just frustrated. Let's put a real answer. And we probably could have kept going with 9. We'd get 19, 33, and 91. None of those would work. But I'm not going to include that for the sake of completion. So we got 8 after 4 steps if we start from 77. And it looks like, if we just mentally do the case for 9 in our head, 77 was the only possible answer here. So that makes it really easy to mark. And certainly, at least the way I did it, really difficult to answer. Yeah. So that concludes D part on the 2011 Friar question number 3. I liked the question up until D part, but I really don't see a better way of doing it. It's just a bunch of sort of arithmetic, and that's not what I think of when I think of a math contest. I mean, sure, there's always some casework you might have to do for a lengthy question, but there wasn't pattern recognition that I could see in that question, and that's, to me, a bit of a shame, because mathematics, and especially this written stuff, these proof style contests, they should be about pattern recognition, about developing techniques or applying ones that you're introduced to. They shouldn't just be, do you know your times tables well enough? And can you do that fast enough? Which is what D appeared to be. Again, if you have a better way of doing this, please leave it in the comments. I love to learn these things. But honestly, I can't see a better way of doing that. So, yeah, that concludes question number 3 of the 2011 Friar. Hopefully you haven't been discouraged and you'll join me for the last question, question number 4. But we'll do that in the next video. I'll see you then.